Hello students, this is Bronsted-Lowry theory. So let's take a look. There's our objectives. I'll skip those for now. So in grade 11 you would have learned, or in Chem 20 you would have learned that according to Arrhenius, acids produce H positive ions. So if you take hydrogen chloride gas, bubble it into water, you get H positive aqueous. H positive is what makes an acid an acid. And so because H positive is present, we can test for the presence of acid. We put litmus paper in the water. If it turns red, it's an acid. That tells us that there's H positive ions in the beaker. He also said hydroxide ions are what makes a base a base. So because we have OH negative in the water, hydroxide, that's what makes litmus turn blue, indicating that it's a base because OH negative is present. So that's the Arrhenius theory. It's pretty good theory, works it gives us predictable results. However, not 100% accurate. For example, if you put NH3 in water, you might predict that it would turn into an acid because we have H positives in the beaker. But what in fact happens is if you drop NH3, dissolve it into water, I should say, and you litmus test it, it's a base, which means there must be some OH negative present. But where did it come from? Because there's no OH in the NH3 formula. So what's going on? Well, we have a new theory, Bronsted and Lowry theory it's called. In this theory, acids are proton donors. A proton is an H positive. It's a hydrogen, which is one proton and one electron, that's thrown away its electron. So it's a proton. H positive is a proton. So an acid is when a substance that throws away an H positive or a proton. So if you see the reaction that I just showed there, the H jumps off the water and goes onto ammonia, which is why it forms NH4 with that positive charge, and why water has gone from an HOH to an OH. In that scenario, acid, the acid, or the thing that donated the proton, is the water, and the base is NH3. On the other side of the equation, if you're going backwards, the NH4 has to give away its H to the OH negative in order to turn back into NH3. So, oops, I went too far. So that's why NH4 positive is a conjugate acid and OH negative is the conjugate base. In the backwards reaction, NH4 positive is throwing away its H, it's the acid. We call it the conjugate acid. Okay, so same thing on this one. You saw that I'm going to back that up. Okay, conjugate acid, conjugate base. Okay, now what is the acid in this case? We have HCl reacting with water. So the HCl has thrown away its H positive, and H2O becomes H3O positive. Okay, so HCl is the acid in this case. Water is acting as the base this time. It's receiving the proton. And on the other side of the equation, if you could go backwards, this reaction actually doesn't go backwards, but if it could, the H3O is turning into an H2O, so it's throwing away its H. So it's the conjugate acid, and Cl negative is the conjugate base. Okay, a conjugate acid-base pair is just a pair of substances that differ by one proton. So the NH3 and the NH4 positive in the top reaction differ by one proton, by one H. Same with the water. In the bottom reaction, HCl and Cl negative are conjugate pairs, and water and H3O positive are conjugate pairs. By the way, H3O positive is called the hydronium ion, and it is a synonym in chemistry with H positive, and you'll see why in a little bit. Okay, what's an amphiprotic or an amphoteric species? That's just something that can act as an acid or a base. So for example, in the reaction, in the top reaction, acid was giving a proton, so it was, sorry, water was giving a proton, so it was acting as an acid. But in the bottom reaction, water was receiving the proton, so it was acting as a base. So the substance water can act as either an acid or a base, okay, depending on the situation. All right, and here's an example of that, the same concept. HCO3 negative can act as an acid. It can give away an H positive like that and become CO3 2 negative, or it can receive an H positive and become H2CO3. So it's an amphoteric entity. Okay, it can act as an acid or a base. Okay, water is the same thing. Okay, let's talk about that hydronium ion. In this subject, we use Bronsted-Lowry more often than we use Arrhenius, and so I say here it's the more correct way of representing acid ions. And a Bronsted-Lowry reaction involves the transfer of one proton from the strongest acid to the strongest base. So we'll show you some examples of this. Okay, so we have a table in the data book. If you turn to pages 8 and 9, these are our acids, okay? And in the column right beside it is our bases, okay? And the top 6 on that chart are called strong acids, everything above the gray line. And the gray line indicates that every one of those strong acids, when they're dropped in water, becomes the hydronium ion, H3O positive. You'll see that more later, how that gray line comes into play, but the top 6 are strong acids, and these are weak acids, okay? An amphoteric entity on this chart, remember, it can act as an acid or a base. Here's an example. The bicarbonate ion, HCO3 negative, is found on both sides of the chart, therefore it is amphoteric. Also, when we get moving here, when we get to the problems that we're going to solve, if the acid is above the base, like in this situation, that means products are favored. And if the acid is below the base, like in this situation, that means reactants are favored. You'll see how that applies in just a second. Okay, now we're going to predict an acid-base reaction. So we're given this potassium acetate reacts with sulfurous acid, and then I would ask you to predict the reaction that will happen. Step 1 is list all the entities present. Potassium acetate dissociates. You can check the solubility table for that. So that's really K positive and CH3COO negative, the acetate ion. And because those have an aqueous, that means water is there somewhere, so H2O and sulfurous acid. Okay, the next thing is to identify all of these on the chart. So we go find them. K, I actually can't find it on the chart. CH3COO negative acetate is right there. Water's in a couple of spots, and H2SO3 is right there. Now, here's another rule with H2SO3. If it's a strong acid, dissociate it or ionize it, break it into ions. If it's a weak acid, don't break it into ions. So H2SO3 is weak, it's below the gray line. We're not going to break it into its ions. Next, identify the strongest acid and strongest base. Okay, so I look at my acid column and I just find the highest one. The highest one is the strongest, so that's that's H2SO3, sulfurous acid. And then I look at my base column. The lowest one on that side is the base. So acetate is the base, the acetate ion. And then we just write the reaction. Transfer a proton. So take your acid plus your base, transfer your proton, and you get HSO3 negative because you've lost an H. And the H carried a positive charge with it. So now the H2SO3 has become negative because it's lost a positive. And CH3COOH. The H attaches at the end. You might think it should be CH4COO, but the way we draw these organically, the H attaches onto that O. Okay, and that's my conjugate acid, that's my conjugate base, and because the acid is above the base, products are favored. Okay, that's example A. Let's look at B. List all entities. So I got sodium bicarbonate, that dissociates into Na positive, HCO3 negative. I've got water present because I see the aqueous symbol, and I've got hydrochloric acid. So then I go find all of those on the chart. So sodium, I can't find, HCO3 negative is there, water is there, and there's HCl. So then I remember this rule: strong acids break up, weak ones don't. HCl is actually a strong acid. It's going to break up to H positive and Cl negative. And now, because we're in Bronsted-Lowry, we have to use Bronsted-Lowry entities. H positive is a synonym with hydronium. So H positive isn't on the chart, but H3O positive is, the hydronium ion. And if you just watch the chart, that means HCl has become H3O positive. So that is my strongest acid. H3O is my strongest acid. HCO3 negative is my strongest base. Okay, and now I just write my reaction. Take my strongest acid plus my strongest base, transfer a proton, and I get H2CO3 and H2O. Acid is above the base, and so products are favored. Okay, last example. Sodium cyanide reacts with potassium bicarbonate. So I've got Na positive, Cl negative, I see aqueous, I gotta have water, K positive, and bicarbonate, HCO3 negative. Let's go find them on the chart. Okay, there they are. All right. Now, where's my strongest acid? Well, I look at my acid column. The highest one is the strongest acid. Oh yeah, I don't see any of those on there. Don't have to worry about that. Okay. Then I go to my strongest acid, reacting with the lowest one on the right, the strongest base. And then I identify my strongest acid as HCO3 negative, strongest base is cyanide ion. And then I transfer a proton. There's my acid, throw away its H, goes over to HCN, leaving me with CO3 negative, conjugate acid, conjugate base. Acid is below the base, so reactants are favored. Okay, so that is how you do Bronsted-Lowry equations. Okay, thank you very much.